Good afternoon, everyone. Can you hear me? Excellent. Okay, well, it seems like the end of the semester snuck up on us. We have a wellness day on Wednesday where classes are canceled. I had forgotten about that last Wednesday. So it looks like we only have one more class left in the semester. We've got today and next Monday, and that's it. So I'm going to get as far as I can with the material on SystemVerilog. I also posted quiz 8 today on Moodle, and it will be due on Monday at 3:55, and then we'll have our final exam. I'll spend some of lecture on Monday reviewing. I'll just kind of go through things pretty quickly, but if you have any questions, you can stop me and ask. And if you have any other questions, it says the quiz will close on Monday, April 19th. Oh, for quiz 7. Oh, so quiz 7 is still. Oh, okay. Ugh. Okay. Yeah, I don't remember why I did it that way. Thank you for pointing that out. Let's see. Has everyone taken quiz? Taken the quiz. Let's see. Quiz 7, 86 attempts. Yeah, it looks like mostly everyone's submitted. I'm going to go ahead and just review the quiz, just because I want to give you a chance to make sure you understand this stuff for the final exam. I'm sorry about that. I don't know why it should have been. It's normally I make the quiz due at 3:55 so I can go over it.
Is it still due at 11:59 today?
Yeah, I mean, if you haven't submitted it, then yeah, you can go ahead. I mean, there's nothing I can do about it now. I want to go over the quiz today so you have a chance to, so everyone's on the same page. The quizzes are designed to be easy anyway. You've got a week to do them, and so I'm not real worried about that. But the final exam is comprehensive, so I want to try to reinforce this right away before you forget about it. Okay, so we've got the final exam is on. Let's see, when's the final exam? Let me. Okay, so the next quiz is due. So our last class is a week from today, Monday. Wednesday's class is canceled, and the final is on Friday, April 30th. So next Friday, and it's scheduled from 4 to 6 p.m. The final exam will be comprehensive, and like I said, I'll run through the material on Wednesday, and if you have any questions or if you need anything clarified, you can stop me then, and if you have any questions outside of class, feel free to send me an email. Okay, so let's see, quiz 7 was about interconnects. It was the second half of the low-level CMOS design lecture. Hopefully you can see the slide there. I've got the first question on there. Copper has a bulk resistivity of 1.7 microohms times centimeters. What is its sheet resistance when its thickness is 0.1 microns? Okay, so remember the bulk resistivity is got kind of a strange measurement, microohms times meters or centimeters or millimeters or microns. And so the idea is when you take the resistivity and you divide it by the thickness, you get the sheet resistance. And because the resistivity is microohms times distance, and the thickness is distance, then you end up with a ohms per square for this sheet resistance. So basically the distance part, the units of measurement in terms of the distance factor out, because you've got the distance in the numerator for the resistivity, and then you're dividing that by the thickness, which is single dimensional distance. So the resistivity here is rho, and T is the thickness, and so R sub square, which is the sheet resistance, which is the resistance per square, is the resistivity divided by the thickness. So 1.7 in this case, you've got 1.7 the 1.7 microohms times centimeters is the numerator, right? That's the resistivity. And you divide that by the thickness, which is 0.1 microns. A micron is a millionth of a meter, or 10 to the minus 6th meters. So if you take the 1.7, you divide it by 0.1, you get 17. So those are the two scalar values there. And then the meters factors out, so you end up with just ohms in the numerator there. And so you've got microohms is 10 to the negative 6, and you're multiplying that by centimeters, which is 10 to the negative 2nd, and you're dividing by micrometers again, micro again, which is 10 to the negative 6. So the 10 to the negative 6 factors out, meters factor out. You end up with 17 times 10 to the negative 2nd power, which is ohms per square, which gives you 0.17 ohms per square. So this one had you might have noticed if you looked at this quiz early, there was a bug in the answers on this one, which I fixed earlier this morning. And if you already submitted your answer when I found the bug, I gave you credit for it. But if you're looking at it, if you looked at it after I fixed it, then it should be good. Okay, so question 2, assume a wire has a sheet resistance of 0.5 ohms per square. What is its resistance for length equals 2 microns and width equals 0.05 microns? So once you have the sheet resistance, you can find the total resistance of the wire by multiplying the sheet resistance times the length over the length divided by width, right? Oh, that's interesting. Okay, Joseph, I'll check that out. It shouldn't. So generally, if I find a bug in one of the questions, I give credit for that question to everyone who's already submitted. So I don't know why that didn't work, but thank you for pointing that out. Let me write this down so I don't forget. Sorry about that. Quiz 6. Okay. Okay, so we've got once you have the sheet resistance, which we do in this case 0.5 ohms per square, you multiply that by the ratio of length over width to get the wire resistance. So in this case, it would be 0.5 times 2 over 0.05. The microns cancel out. You're just left with ohms there, and that gives you 20 ohms. What is the aspect ratio of a wire with thickness equals 0.4 microns and width equals 0.2 microns? That's just the ratio of thickness to width, which would be 0.4 over 0.2, which is 2. This one is a little hard to remember because I don't know. I would think it would be width over thickness, but it's thickness over width, so I get tripped up by that myself. But in this case, you just remember it's thickness over width, so in this case it's 2. And that's actually a pretty typical aspect ratio. So wires are really thick on compared to their width on modern semiconductors. Okay, the next question, consider a wire with length equal 10 microns, width equal 0.2 microns, thickness equals 0.2 microns, and has a height of 0.01 microns above the substrate, and the oxide separating the wire and substrate has a dielectric constant of 3.7 E0. E0 is the permittivity rather, of vacuum. What is the wire's capacitance? So you just plug all those numbers into the equation here that was in the slide. Now this equation is a fitted model for the capacitance. So this is based on empirical data. Someone at some point did some measurements and they came up with this equation to model the capacitance. There's probably a more accurate way to do this, but this is a way to just get an approximation. So this would, you just plug in all the numbers. So it's and you have to make sure that you have the significance of all the units in there correctly. So the width over height, thickness over height, the units will cancel out there. Those are all in microns. And then the 3.5, you just plug that in for the sigma oxide, and the length is obviously in a distance, but somehow, and to be honest, I'm not actually sure how this works out. In fact, I don't know if it works out units wise, but you would think that the final units here would be whatever the units of the dielectric constant multiplied by length is. But in this case, we're assuming that this thing evaluates to farads. So in this case, once you work it out, it should come out to be about, it's actually 9.7 times 10 to the negative fourth farads. But if you look at the answers, the closest one there is a 1 millifarad, or 1 times 10 to the negative 3 farads. So it's just rounded up. What is the delay of a path consisting of a 10 ohm inverter driving a wire with capacitance of 100 femtofarads and resistance equals 100 ohms? Driving, I should have said capacitance equals 100 femtofarads, but yeah, you get the idea. Driving another gate with load capacitance 10 femtofarads. Use the pi wire model with one lump. So the pi wire model would be the center portion here. So you take the capacitance and you divide it in half. So let's see, the capacitance was 100 femtofarads, so you divide that into 50 femtofarads and 50 femtofarads with the resistance in between, and that shape looks like a pi, looks like a Greek pi. And then on the left-hand side, we have the driving gate, which is a 10 ohm gate, or a 10 ohm inverter. And the right side represents the input capacitance for the load, the gate load, whatever gate's input we're driving. And so it says that's just 10 femtofarads. So in order to calculate the delay, it's basically just capacitance times resistance, but because we have this type of circuit where we have two resistors in here, we need to calculate the Elmore delay. And so for the Elmore delay, you take the 10 ohms for the driving gate, and you multiply that against the 50 femtofarad capacitance on the left side of the wire model. And femto is 10 to the negative 12th. So then we calculate the second part on the other side of this resistor, the wire resistance, as having a total resistance of 10 plus 10 plus 100, right? So that's the plus 10 plus 100, right? That's the total resistance from here over to this side. And then the total capacitance there, these capacitors are in series, so the total capacitance there would be 50 plus 10, or 60 femtofarads. So it would be 10 ohms times 50 femtofarads plus 110 ohms for the series resistance of the two resistors, multiplied by 60 femtofarads. So that would be, it ends up being 7.1 times 10 to the negative ninth. Well, what's the unit there? What's seconds? So that's picoseconds, 7.1 picoseconds. 10 to the negative ninth is pico. Okay, how much energy is required to transmit 1 bit on a wire with 2 femtofarads capacitance at 2 volts? This is actually really easy. You just multiply the capacitance by the voltage squared. So it would be 2 femto, 2 times 10 to the negative 12, times 2 squared, and that gives you joules. It's a unit of energy. So that's going to be 8 femtojoules. Now, if I asked you about power, if you had like a frequency, a bit switch frequency or an operating frequency, then you could multiply, basically bits per second or transitions per second by this energy and get power. So like, for example, like you might remember from your 212 class that you can estimate the dynamic power consumption of a chip as the total capacitance multiplied by voltage squared multiplied by frequency. So if you add the frequency term, you get power. If you leave that off, you're just going to have energy. In this case, just 1 bit. If I asked you, if I said you're sending 1 billion bits, then you would multiply this by 1 billion, and you would get energy for 1 billion bits. But if I said you were sending bits at 1 gigabit per second, because you have that per second in there, it's a rate. Then this you would multiply that by this, and you would get power. So, like for example, so if I said 1 gigabit per second, you would just multiply this by 1 times 10 to the gigabit, 9th power, right? Yeah, 9th power. So you'd multiply this by 10 to the 9th power bits per second to get the power for this wire. Okay, so yeah, 8 femtojoules per bit in that case. Okay, next question. Consider at wire A switching from 0 to 2 volts next to an undriven wire B. So in this case, wire A is the aggressor wire, wire B is the victim wire. The coupling capacitance is 10 femtofarads. Wire B has a ground capacitance of 20 femtofarads. What is the voltage change on wire B during the transition on wire A? Transition on what? Yeah, on wire A. Right. So for this, you just use the equation for the delta V for the victim, where the victim is a undriven wire. So it's delta V victim is the coupling capacitance divided by the sum of the ground capacitance and coupling capacitance, and then multiplied by the change in voltage of the aggressor. So this one's pretty easy when you have the undriven aggressor, right? So this would be basically 10 over 30 times 2 volts. So 1/3 of 2 volts, or 0.67 volts. So that's a pretty big it's a pretty big influence, right? The aggressor is able to get the victim to change its voltage by 0.67 volts just by switching 2 volts nearby. But if the victim is being driven by a gate, then it's a different story. You use a different equation. So that's what this next question is about. Consider wire A driven by a 20 ohm gate switching from 0 to 2 volts next to wire B driven with a 50 ohm gate. The coupling capacitance is 10 femtofarads. Wire A has a ground capacitance of 20 femtofarads, and wire B has a ground capacitance of 15 femtofarads. What is the voltage change on wire B during the transition on wire A? So for this, you need to calculate this K term, which is basically the ratio of strengths between the aggressor versus the victim. So it's the resistance, or the effective resistance of the aggressor, of the gate driving the aggressor wire rather, on the numerator, and in the denominator you have the effective resistance of the gate driving the victim wire, and then you multiply each of those by the respective ground capacitance plus the coupling capacitance. So you have ground aggressor and ground victim. So the R sub aggressor is 20 ohms, R sub victim is 50 ohms, and then the ground capacitance of the aggressor is 20, because it's wire A, 20 femtofarads. The ground capacitance of the victim is 15 femtofarads, and the coupling is 10 femtofarads. So you end up with a K value of 0.48, and then you go back and you calculate the coupling capacitance divided by the victim ground capacitance plus the coupling capacitance multiplied by the change in voltage of the aggressor, just like we did before with the undriven victim. But in this case, we also include this third term, which is 1 over 1 plus K. And so in this case, we've got the 10 farads, which is coupling, over 15 farads victim ground capacitance or victim ground capacitance, and then plus the coupling capacitance. So that's 10 over 15 plus 10, or 10 over 25. And then 1 over 1 plus K would give you 1 over 1.48, and then the 2 volts swing for the aggressor, and you end up with 0.54 volts, assuming I did that right. Let me know if you find a mistake there. Okay, next question. Assume wire A and B, both having ground capacitance of 20 femtofarads and a coupling capacitance of 10 femtofarads, are switching opposite from one another. What is the additional delay capacitance? So this is the Miller effect. So, this is additional capacitance, not that adds noise, but adds delay. So this is delay capacitance. This is slowing down the wire. So this is the way that parasitics slow down the wire. So in the previous two questions, we were talking about noise. So you've got another wire that's adding voltage, that's adding noise, right, to the victim wire. In this case, we're just adding delay to the victim. Or actually, well, I guess this would be for both, actually, delay on both wires. So if they're switching opposite, so if you have one wire going from 0 to 1 and the other going from 1 to 0, then you're seeing 2 times VDD switch on any one wire relative to, or on one wire relative to the other. And so in that case, you get this additional capacitance, which is the ground capacitance times or plus 2 times the coupling capacitance. So in this case, you take the ground capacitance with 20 femtofarads and you add 2 times 10 femtofarads to get 40 femtofarads of delay capacitance here. So I might ask you on the exam, I might say that there's no relative voltage swing, or they're changing, they're changing together. They're both transitioning from 0 to 1 or 1 to 0. Or you can just have one wire switching its state and the other wire remaining constant, in which case your delta V there on the wire is just VDD or negative VDD. And so the additional delay you get there is just the coupling capacitance. Okay, and then last question, what is noise margin low? So this is underscore L. This is meant to represent a subscript, and NM sub L for an inverter with VIL. Actually, that should be underscores there as well. V sub IL and V sub OL. 0.3 volts and 0.1 volts. So remember that when you have a gate, you have essentially different thresholds for 0 and 1, depending on if it's the input or the output, and also depending on whether it's low or high for both, right? So in this case, what this means is the VIL, V sub IL, is the voltage, the highest voltage that represents a logic 0 for the input of a gate. And VOL is the highest voltage for logic 0 on the output of a gate. So the noise margin is just the difference. So in this case, it's just 0.3 minus 0.1 is 0.2. So that's pretty straightforward. The high side, for the high side, you would have to reverse these terms. So if I asked you to calculate the noise margin high, Nm sub h, you'd have to take the lowest high voltage for the output minus the lowest high voltage for the input. So they would be swapped, right? But yeah, so basically it's the difference between the input and the output logic thresholds on both the high and the low side. And so we didn't talk very much about this in the lecture, but the idea with this is when you're calculating this crosstalk noise, which is the yeah, it's this, when you're calculating crosstalk, as we did, I think it was in questions 7 and 8, you have to be careful that the crosstalk doesn't exceed these noise margins, right? And if they do, then what do you do? What do you have to do? Well, you could move the wires farther apart, which would reduce the coupling capacitance, or you can put bigger drivers, put bigger gates to drive them, to drive the wire that's exceeding its noise margin. So the idea is that this is one of the factors that plays into performance and the design of these semiconductors, these processors. Okay, any questions? Okay, good. Let me switch over here to okay, so as I mentioned, I've got a quiz on the Verilog material. I had to kind of guess though how far we're going to get today. I'm going to get as far as I can. I'm probably not, well, I'm certain I won't get to state machines, unfortunately, but I'm going to try to get through as much of this material as I can. And if you're interested in this, don't worry, you'll see SystemVerilog again and in much more depth when you take CSCE 611. So this is just intended to be an intro, and hopefully by presenting a little introduction to this in 317, you guys will have you'll be prepared when you see it again in 611. Okay, so just to quickly review what I talked about. Wait, you can see the slides, right? Can you guys see that? Can you see the HDL slides? Ah, yes, I see it. Okay, good. All right. Okay, so there's several different HDLs, but the two that are most popular by far are actually the oldest ones, surprisingly, developed in the early 80s, VHDL and Verilog. They've been updated though. There have been other ones that have come along, but it's really strange. It's surprisingly difficult to get new HDLs widely used and accepted. I don't know why that is. Probably the most famous one was developed by MIT recently in the last 10 years or so, and it was called BlueSpec. And that was meant to be the end-all and be-all HDL, but it never really caught on. There's another one now that's from Berkeley called Chisel, but actually Chisel is not really an HDL. It is a domain-specific language that is converted to HDL automatically. So it's used to generate VHDL essentially. So it's, you basically, you write chisel and then you compile it to Verilog, and then, then you synthesize or simulate the Verilog. So it's not exactly an HDL. These HDLs, VHDL and Verilog, you can simulate them directly, and you synthesize directly. You don't have to go through another language, although the compilers probably have some intermediate representation internally, I'm sure. But anyway, VHDL is VisiC. HDL, Verilog is, I don't know what Verilog stands for. I don't know where that came from. But the current version of it is actually called SystemVerilog. So sometimes I'll just say Verilog, but in this class I'm actually teaching SystemVerilog. Probably the most noticeable difference between Verilog and SystemVerilog is that we use the logic type in SystemVerilog, and in Verilog you use the wire and the reg type, data type. That's the most obvious difference between the two. There's other differences, but that's the one that's most probably noticed the quickest. Okay, so I mentioned HDL can be simulated, and the simulation is how you test it, how you test the code, how you validate it. So when you simulate VHDL, you're simulating a hardware design. So the simulation is performed with a discrete event simulator, meaning that you're not like running code like you would software. You're simulating it and looking at the state of the signals over time. So you generally will look at them most often in a waveform viewer, and we introduced you guys to this in labs 1 and 2. So the trace file that you read in the labs in this course was similar to the type of trace file that's generated by a simulation, an HDL simulation. So you can read those and you can convert it to a table like a listing. Or you could, show them on a waveform viewer, as I show in this lecture. Then the synthesis is where you take the HDL and you lower it down into a netlist or a schematic or basically gates connected with wires. Now they don't have to be gates. They could be whatever your primitive hardware components are that you're targeting with the synthesis. So it might be, in the case of an FPGAs, it may be lookup tables, for instance. But usually it's like a kind of a logic gate level description. You don't go. In other words, what I'm trying to say is you don't go to transistors. So we looked at transistor level designs in the last lecture, but when you synthesize HDL, you're not going down to the transistor level. You're going down to the logic level. And then if you're targeting an FPGA, you would allocate individual lookup tables, which are basically reprogrammable gates on the chip, and you would allocate those and map the logical gates that are the output of the synthesis to the physical gates on the FPGA. Or if you're targeting an ASIC being an application-specific integrated circuit, like a custom chip, basically an integrated circuit, then you would be targeting a vendor-supplied logic library, or what's called a cell library, where the cells are the logic gates. Now those logic gates are implemented at the transistor level, and then they're drawn in layouts. They're drawn in the layers, the diffusion areas and the gates and the wires that would actually be fabricated. But the difference is if you're targeting a custom chip, you can instance any arbitrary gates you want in there because they'll be fabricated. So it's a little bit more flexible. You can take whatever gates are in the netlist and just essentially place them anywhere on the substrate you want them, and then together, all those gates together, put in and connected, will be sent off to the fabrication place, and then they'll send you back a chip. So the point is that simulation, synthesis are the two main tools you use on HDL code. There's also two styles of HDL code, behavioral and structural. Behavioral is describing what a module does. So that's looks more like code. Essentially, it's you can write in Boolean logic or arithmetic or state machines. little multiplexers, and I showed you some of that, or RAMs. And then there's structural, which is how you take modules and you instance modules and you connect them with wires. So you're basically just building a schematic, but not, you normally, when you think of a schematic, you think of a picture, right? A picture, like a block diagram, like actual modules that are drawn in a drawing and connected with lines that are meant to represent wires. But in Verilog, it's in code, so you're not actually drawing a picture, it's all in text form, and that's structural HDL. Now you might say, well, why, I mean, if this is an artificial distinction, why do we care about this? Well, it's two different styles, essentially, of the code. So structural code is where you're basically just instancing and connecting modules, and behaviorals where you're actually, implementing, low-level behaviors. Most of the code you'll see is going to be structural. So this is an example of a module called example that has 3 inputs and 1 output, and it has 1 assign statement inside that actually is behavioral HDL. So this behavioral HDL in this case is just Boolean logic written in the style of C or Java. And it's inside this module, which is kind of like a class. You can think of it kind of like a class in Java. And there's a pinout on the top, or a port map, not port map, port list. So you've got 3 inputs, A, B, and C, and an output Y. And so that's the top level. That's the interface for this module. So anyone that uses this module will have to connect wires to the ports A, B, C, and Y, and it wouldn't see the assign statement, because it would be, that part of it would be internal to example. So then there's the logic type, which is, in this class, is the only data type we'll use. The logic type is meant to represent a bit or an array of bits if you have a multi-bit logic type. It's a 4-state. It has 4 possible values or states, 0 and 1, obviously, because it's it's meant to represent a bit. But there's also X and Z, which are special values. X is means either don't care if you're actually setting a signal to X, like in your code. Like, so if it's you setting something to X, it means don't care. But if it's the simulator doing it, it means that the value is in conflict, meaning that it's being double driven. There's something that's trying to set it to 1 and something else trying to set it to 0. Or it could mean uninitialized. It could be like an output from a RAM or a flip-flop that hasn't been initialized. So that part is kind of, unfortunately, a little ambiguous. In order to figure out which one it is, you have to investigate where the X is coming from. And then there's also the value of Z, which is the 4th possible value you can assign to a logic type, and that means high impedance. So if you have something driving a signal as 1 and something else driving the same signal with Z, then you would not be in conflict, because only one, in that case, you'd only have one entity setting a signal to something other than high impedance, right? I didn't explain that very well, but the idea is that high impedance is used for tri-stating. So so it's a way that you can have 2 things setting one signal, as long as only one of them is actively setting the signal and the other ones are high impedance. So Z is a way to say, I want you to disconnect. Like if I set a value to Z, it means, yeah, I can set this wire, I can drive this wire, but at the moment I want to disconnect myself from it. So that's high impedance. Okay, so we've got this example here. This is the same one I showed. Yeah, so this is the same one I showed earlier, but this is now showing the simulation. In this case, it's a waveform. So we've got the horizontal axis is time, and then the vertical axis is meant to represent kind of like an oscilloscope, low and high, 0 and 1, representing the values. So to read something like this, you have to basically draw a vertical line down, and where that line would, actually the vertical line is over here, it's this blue line, it just happens to be over to the right hand side. But if you draw a vertical line, it's capturing what the states of those wires are at that moment in time. So in this case, it's 480, 640. So that's 160 difference, and then there's 1, 2, 3, 4. So I guess that's 40. Looks like 40 nanoseconds per line here. Oh yes. Is there any other software other than Quartus to simulate Verilog code? That's a great question. There is. There's actually Quartus doesn't simulate. So simulators are. You would think that there'd be a lot of simulators around, you know, because this is how every chip in history has been made. Basically, is having to design it kind of at the, you know, behavioral level, you know, at the logic level, and then, and then of course at some point generating all the transistors and the layout, right? But there's not actually, in my experience, there's not many. There's very few of these simulators, and the ones that are actually used in industry are commercial, and they're expensive. You know, so Mentor Graphics has a software called ModelSim, and Synopsys has a software called oh God, what is it called? I'm drawing a blank. But there's two big companies that make this. There's the Mentor and Synopsys. Yeah, I was going to get to that, Charles. So I can't remember what the Synopsys one is. But anyway, if any of you guys get a job at IBM, Intel, or any company that actually makes chips, you will you're going to be using the either the Mentor or the Synopsys software. Those are the industrial ones. As Charles indicated, there are also open source tools, and we've used them. There's Icarus Verilog and there's Verilator are the two most common open source tools for doing this simulation. We actually used Verilator in this course last spring, but it didn't go over very well. The students didn't like it very much at all, because it's tough to use. And it also has some things about it I didn't like either, because Verilator is, as Charles mentioned, Verilator is actually it's this kind of cool concept where instead of just reading your HDL into a simulator and simulating it, it actually converts it into C code that you can compile and run. So it takes your Verilog code and it kind of combines it with a simulator somehow, and then outputs another C program, a downstream C program, which you can compile and then run it. You know, it basically combines your code and the simulator together in one glob and runs it. Whereas the other simulators are separate tools that read in your code and run. But anyway, yeah, hopefully those are the only four I know of, actually. I don't know of any. There might be others, but there's the two commercial ones and the two free ones, and that's it, which is kind of shocking, like I said, because this is something that anyone that's building a chip would have to do. I'm sure there are others that I'm not aware of, but those are I only know of four. Okay, and yeah, Charles dropped some links to those in the chat if you're interested. Okay, so that's the simulation. So yeah, so anyway, in this case, we've got 800 nanoseconds worth of simulation, and each one of these lines is looks like 40 nanoseconds. And so if you drop a cursor, or a cursor being a vertical line that cuts through vertically, then the where that intersects on each of these four would be the state of those signals at that moment in time. So if I drop a vertical line here at 440 nanoseconds, where my mouse cursor is at, then at that moment in time, A would be 1, B would be 0, C would be 0, and Y would be 1. In this case, someone is stimulating A, B, and C to go through a counting sequence. So all 8 possible values of A, B, and C are set at some point. It looks like every 80 nanoseconds, the inputs change here. I don't know who's setting that. There must be, either the simulator is doing it through simulation commands, or someone wrote a test bench, another design that's actually providing the input. But you can see that this module it's the design being tested, and the only signal that this module is actually setting is Y. So Y is the only thing that's actually being set by this. A, B, and C are being set by someone else who are, running through test cases on this guy. And then this is the synthesized net list. So, and this is only one possible way to synthesize this. There's other ways that there's other combinations of gates that would achieve the same functionality. But in this case, this was synthesized by Quartus. Quartus is the software that we'll use in 6.11. So you guys will get an opportunity to actually do this, to convert this into gates, if you, assuming you're taking 6.11. And this is one possible way to convert this code into a physical arrangement of gates. Now, these are still logical gates. These show wires and inputs and outputs and gates. But these are still logical gates, because to actually build a chip, you would have to take these logical gates and actually put them into a physical gate, associate them with physical hardware. That's called mapping. Okay, so Verilog Syntax is kind of similar to Java. I mean, at least it has some commonalities with Java, right? It's case sensitive. It uses the same comments. White space is ignored. I think the naming restrictions might be different. So it's noted here that no names can start with numbers. But I think everything else here is fairly familiar to you. Okay, so now let's look at some structural or mixing behavioral Verilog with structural. So you've got this AND gate, it's got one line of behavioral code, and then my design, which uses the AND gate. So in order to use other modules, you need to be able to connect something to their inputs and outputs. So in this case, we have four internal signals, A, B, C, and N1. And then in order to use this AND gate, this AND3, we just say AND3 space, the name of it, AND gate, which can be anything. This is just for, the only time you'll see this AND gate is in simulation. Or yeah, if you're simulating, you would use this name, but this doesn't actually, this has no meaning once you do synthesis. Once you convert this to hardware, the name of this thing is irrelevant. So you've got AND3, AND gate, so I instance an AND3 module, and then I need to connect its pins or its ports, A, B, C, and Y, to signals that are visible inside my design. So I'm going to connect the Y port on the AND gate to this N1, which is an internal signal, which I declared as a logic here. Notice the syntax here is period, then the formal port name, and then in parentheses you give the actual connection to that. And they don't have to be in the same order as they're listed in the input and output pin listing or port listing for the module that you're instancing. So, up here I had A, B, C, and Y, but I'll connect them in the order of Y, B, A, and C. It doesn't matter. Doing everything on one line like this can get very unreadable once you have very big sets of inputs and outputs, which is common in Verilog for larger, more complex designs. So you can, because white space is ignored, you could put each one of these connections on its own line if you want to. Okay, so here's a trying to extend that example out a little bit and show it graphically. So, and by the way, just to be clear, the reason I'm showing this is because when you're doing structural Verilog, it's actually kind of unnatural to represent schematics using text. When I first started teaching this class, we used a graphical editor to draw schematics, to draw all of the structural code was drawn. I stopped doing that because the tool we were using, there's a lot of tools that allow you to do that. And so I was afraid that I was just teaching the students just for one tool. And I was in the way that you do the graphical design, it differs between different tools. There's a lot of variety of graphical, what they call schematic capture or schematic entry tools. So I didn't want to, just train everybody on one specific tool. We were using one of the mentor tools called HDL Advantage. But the other reason I stopped doing that was because I started working more with people in industry. I was working with a group at a company called Convey, and then I was working with a group at TI, and I found out that in industry, no one does graphical schematic entry. It's much more common, in my experience, to just write straight code. And this is kind of similar. I don't know if you guys are familiar with like doing web page design. Like, there's ways that you can do, you can use graphical tools to design a website, but professional website designers don't do that. They generally write in a text editor. So it's the same kind of thing here. So I switched to this textual, but the problem is that you have to understand how the structural code would look if it were done graphically. So that's what I'm trying to show here. So basically, you've got this design called NAND3. You've got A, B, and C are inputs and Y is an output. So this would be like this is meant to represent a symbol, a NAND3 symbol, a block that would be on a block diagram, right? And so you've got the external interface, A, B, C, and Y. Normally these blocks, if I were using this AND3 in a schematic, it would be opaque. It would be, a black box. But I'm going to show it kind of as a glass box so you can see what's going on inside. And what's going on in there is I've got N1, which is an internal wire, and then I've got an AND gate and inverter that I instantiate in there. Each of those have their own pinouts. And then I'm going to connect all of the pins of the internally instanced modules to either a top-level input, A, B, C, or Y, of the NAND3, or to internal signals like N1. Now you would use internal signals, you always use internal signals when you want to connect modules internally, right? You want to connect one module to another, you have to create a wire to connect them, and so that's what this N1 is meant to do. So I've got ABC of NAND3 are going to be connected directly to ABC of the top level input on NAND3, and then the top level output Y is going to be connected to the Y of the inverter, and then the Y of the AND gate and the A of the inverter, so the output of the AND gate and the input of the inverter are connected to this N1 internal signal. So the point of this is that we've got the inverter has an output called Y, and so if I look at Y inside the NAND 3, and then I drill down inside the inverter and look at its Y, that's the same signal. But if I look at the Y of the AND gate, if I'm inside the AND gate and I'm looking at Y, that's going to be the same signal as N1 inside the AND gate. Sorry, inside the NAND. Sorry, I should have named these differently. It's kind of confusing. So inside the NAND 3, which is my, top design here, I've got N1. Inside the AND gate, it's called Y. But it's the same signal. So when this is synthesized, all of these signals are going to be, this hierarchy is going to be flattened. So there won't be any, modules anymore when you convert this to hardware. It's just going to be a mass of gates and wires. And so if you were to look at this design after you synthesize it, this wire, you don't know what name that wire is going to have. The synthesizer will give it a name. It might call it N1, it might call it Y, but you don't know. Or it might just give it a machine-generated name. But that's the confusing part, because all of these names and this hierarchy of modules is all just there for the convenience of the designer. But none of that stuff actually exists in the actual hardware. In the hardware, it's just a big mass of gates and wires. Okay, so then this is the simulation. So when you connect wires to pins on a module, that's often called the port map. Now in Verilog, you actually spell out port map, believe it or not, because Verilog is a Pascal-derived language, and it's meant to be self-documenting. So, like if you declare a function, you actually write function, or if you're declaring an array, you actually write array. And instead, if you actually have a bit range, like 10 down to 5 or 10 down to 0, you would write 10 and then the word down to 0. Verilog is a denser code. It doesn't have a lot of those keywords in there, but even so, I still call this a port map, even though I guess you could argue that's a VHDL concept. But the port map, the idea is that I'm mapping ports to signals inside NAND. Okay, so now I've got a few examples here. These aren't on the slides on my website. I have to re-upload these. But these are some examples I added today from previous quizzes and exams I've given. So this one I think this is an easy question. Assume the following Verilog module. It gives the module. How many total bits comprise the inputs? Well, there's two inputs, A and B, and each one of those is 1 bit. Yeah, and actually, this is not written in SystemVerilog, because I need to say input logic AB. You can actually get away with eliminating. You can just say input AB and output C. But the problem with doing, in fact, if you did that here, it would be fine. But the problem with doing that is if you have a construct called an always statement inside this module, which I'm probably going to get to on next Monday, or I might actually get. Let's see what time we got here. I might get to always statements. But anyway, there's a specific type of construct that if you use a specific type of construct, then you do need to have the logic there. So I always just write, input logic, output logic. Anyway, how many total bits? There's 2, A and B. Each one is 1 bit. Okay, here's another example. Assume the following Verilog module, and again, I say Verilog, I really mean SystemVerilog. I should say SystemVerilog. I got this from an old exam, and I only started teaching SystemVerilog recently. I used to teach VHDL, and then I went to Verilog, and then I went to SystemVerilog. So some of this stuff is a little out of date. So assume the following SystemVerilog module. That previous slide should also say SystemVerilog. Okay. Fill in the missing values from top to bottom for the test. It doesn't have to be from top to bottom. It only says that because of the multiple choice in Moodle. Fill in the missing values for the test vectors. Test vectors meaning just test cases for testing module AAA. So, so I haven't talked about this yet, the notation here, but this means 1 bit in binary 0. So A is 0, B is 0. So A is 1 bit of 0, B is 1 bit of 0. So what is the expected value of C? So just imagine like I'm testing this, and I've got this test case where I'm saying 0, 0 for A and B. What do I think C is going to be? Well, according to the logic, it's not A and B. So the only way that C is, excuse me, the only way that C is going to be 1 is if A is 0 and B is 1, because that would give you a 1 and 1. So if A is 0 and B is 1, then I would expect C to be 1 bit binary 1, and in all other cases, it should be 0. So this would be a way I could test this guy, is I give it all 4 possible values for A and B. I basically set those somehow, and then I look to see what the output of the module is, and I compare it to what I expect it should be. So that's what you should get if you simulate this module. Okay, here's another example. In this SystemVerilog code below, to what value is signal A set? Okay, so now I've got 2 modules. Where do I start? Where do I start even reading this thing? Well, if you look at module bottom, it just has one line of behavioral code, and then module top, I instance a module of type bottom in there. So top is the top level, is the top of the hierarchy, and bottom is a leaf node. It's kind of like there's the bottom as the lower level. So I think it's easiest to look at this from top down. So let's start with top. So inside top, you've got logic, internal signals Y and A. You have, and there's no inputs and outputs into or out of top. So top is like a test bench essentially. It's kind of it's a top level design that runs itself. So I've got Y and A, and then I'm going to assign Y to be 1 bit, binary 1. And then I'm going to connect Y to the input on bottom, and I'm going to connect A to the output. So this is obviously meant to confuse you, because basically I'm going to put Y in for A, and I'm going to put A in for Y on the bottom, right? So what value is signal A set? So A is connected to the output of bottom, and the input of bottom is a 1. So if you look at bottom and you say, okay, the input is A is 1, I'm going to take the complement of that to get 0. I'm going to set that to Y, right? And then back to top, Y is what's driving A. So A would be 1, right? So basically A would be 0, rather, sorry. So bottom is basically an inverter, right? So I've got an inverter there. I got Y. I set it to 1, I connect it to the input of the inverter, and then A is the output of the inverter, so that would be not 1 or 0, right? So A should be 0 here, inside top. So the point of this is that you have to be careful of the port map, and so you have to recognize here that A and Y are reversed in top relative to bottom. Hopefully that's not too confusing. That's not common to do it that way, but this example is intended to show that the signals have different names at different levels. Okay, here's another example. In the SystemVerilog code below, to what value is signal A set? Same question, same bottom module. But now we've got one additional line here in the top module where I'm assigning A to 1. Uh-oh, now we got a problem, because A inside of top is being driven by this assign statement. It's being set to 1. But we know that this bottom module is also setting A through its output port, and it's setting it to 0. Because it's taking whatever Y is and it's inverting it and using that for A, or complementing it rather, I should say, right? So now we've got a problem, because inside top, A is being set to 1, but it's also being set to 0 by, so you've got behavioral code setting it to 1, and you've got structural code setting it to 0. So this is a conflict. So you can compile this and you can simulate this, no problem, except when you go to simulate it and you look at the value of A, you'll get an X. A will be X in this case, conflict. Okay, then let's see, these are, this next slide shows 2 new concepts. One is that you can have multi-bit logic, which is common. You have to use this weird syntax, like in this case 3:0 means I want A, B, basically the 2 inputs and the 5 outputs are all going to be 4 bits, because we've got bits 3 down to 0 for each of those. Now, as far as I know, the 3:0 can also be 0:3. It makes no difference. I used to think that reversed the bit order, but it actually doesn't. But the convention is to use the left number is the bit number of the most significant bit, and the right number is the bit number of least significant bit. And then so the most significant bit number minus the least significant bit number plus 1 is the total number of bits. So these are 3 down to 0 means 4 bits. So you can see when you simulate it, each one of these guys is 4 bits. And then also notice that there's 5 lines here of behavioral code that assigns y1 through y5. And I'm just doing these logical operations. And you might say, wait a second, what does an AND do when you have 4 bits? It just does an AND between each of the corresponding bits in A and B. So for example, if A is 0010, as it is right here, and B is 1110, then if I were to AND those, the answer would be 0010 because it would only be there would only be a 1 bit when the corresponding bit is 1 in both A and B. In this case, the only bit that's 1 in both A and B is bit 1, which is the second bit from the right. So if I look at Y1, you can see that, yeah, the answer is 0010. It's what you'd expect if you did a bitwise AND there. And then I talked last time about the conditional assignment. This is a ternary operator where you have a condition followed by a question mark and then an expression that will be the is what the whole conditional statement will evaluate to if the condition were true, and then a colon, and then the value for the conditional statement or the ternary statement if the condition is false. So in this case, I'm doing this to create a mux, and the condition is S, which is the select, and I want to assign Y to be D1 when S is 1 and D0 otherwise, which creates this mux. Hopefully you guys remember muxes from 211 and 212. These are the very commonly used building block in digital designs. Basically, it allows you to route either one of these two inputs to that output depending on the select. So you can see that in this case, the inputs and the output are 4 bits each. The select is only 1 input because there's only two ports on the mux. So for example, if we look at where the cursor is located here, and notice too in the simulator we've got a cursor. It's this vertical line, and you can see the value at that moment in time where you've got the vertical line is shown here on the left. So D0 is 0010 and D1 is 1110 at that moment in time, and the select is 1. So the Y is going to reflect whatever's coming into D1 because of the select being 1, and you can see that's what's happening. Y is 1110, which is matching D1 because the select is 1, and so D0 is getting is not making it through the mux. Okay. Okay, I'm going to skip that for now because I think we've already covered that stuff. Okay, so so Verilog, like any language, SystemVerilog rather, has operator precedence. So basically an order of operations, and that's shown in this table. The highest precedence is the not, the complement tilde. Then you've got multiply, divide, modulo, and then add, subtract, and then your shifts. Notice there's 2 types of shifts. There's the shift operation, which hopefully you guys know from Java and C. But then there's also an alternative way to do shifting with, instead of less than for a left shift, for instance, there's less than less than for an arithmetic shift, left shift. Now, why do we need, do you have an arithmetic shift in Java and C? Well, you actually do. But you don't need to have an arithmetic shift operation in Java and C, because in Java and C, the compiler knows what kind of shift you're doing based on the type of the value being shifted. So if the value being shifted is a signed number and you shift it, it'll do an arithmetic shift. And if it's an unsigned number, it'll do a logical shift. But you don't have the benefit of those types in Verilog. You just have logic in Verilog. So as a result, the compiler has to provide a way for the programmer to specify whether you want a logical shift or an arithmetic shift. And you probably remember from 212, a logical shift is when you shift zeros in, whereas an arithmetic shift really only applies to a right shift. and you shift in the sign bit, the original sign bit. Now you might say, wait a second, if arithmetic only makes sense for a right shift, then why is there a left arithmetic shift? That's there just in case if you do a left arithmetic shift and the shift amount is a negative number, then that translates to a right arithmetic shift. Right? Okay, so then there's comparison operations, same as you're used to, and then you've got equal, not equal, then your bitwise logical operations, and then the ternary operator, lowest precedence. This slide is in here kind of just as a reference for you if you need to look that up. Okay, and I talked about this a little bit already, but in Verilog, there is a way, whenever you have a scalar constant, when you have a number, just a number, inside your code, it's important that you specify to the compiler how many bits that number is. So if I just say 5, and I put a 5 in my code, if you don't put a width, number of bits, that 5 is encoded into, then the compiler will just assume that it's 32 bits. But you don't necessarily always use 32-bit numbers in Verilog. So there's a way to specify that. So for example, you would be, like in this case, if I have the value 5, I could put 5 in as little as 3 bits. So if I did want to put it in 3 bits, or I wanted the compiler to understand that that value 5 is a 5 in 3 bits, then you just type 3 apostrophe, and then the number 5 itself, if you're writing in C or Java, it's assumed that that is a decimal number, but in Verilog, sometimes you want to write hexadecimal or binary or Java. Now you guys know from, in C and Java, you can do hexadecimal with, if you put a 0x in front of the number, right? But in Verilog, you would put H, like shown down here, right? So this number is 8 bits, and then AB in hex. So you put 8 apostrophe HAB. Why not use 0x? I don't know. I don't know why they didn't use 0x. It's different. Likewise, you can do binary I don't know if you could do binary in Java, but you can definitely do it in C, where you put you use the prefix 0b. But in Verilog, it's B. So if you have a 3-bit value with the number 5, but you want to show 5 in binary, it would be 3 apostrophe B101. And then likewise, there's octal, which is an O, and that's just base 8. So a 6, now an 8, base 8, by the way, will associate 3 bits for every digit. So in this case, I have 6 bits, 6 apostrophe, and then O, octal, 4, 2. The 4 and the 2 are 3 bits each, and that makes sense because there should be 6 bits in total. And so that would be the value of, in binary, it would be 100010. So the 4 is 100 and the 2 is 010. In decimal, it would be 34 because it would be 4 times 8 plus 2, right? 34 in decimal. So as far as I know, there's only 3 bases. Sorry, 4. Binary, octal, hexadecimal, and decimal. There's 4 different bases. So that would be B, O, H, and D. Just notice the D for decimal here. In hexadecimal, each digit would be 4 bits. So in this case, I've got AB, and so that would be, it's 8 bits in total. Now, just because you have 2 hex digits doesn't mean that you have to have 8 bits, because if the first digit of this, if I had a 2-digit hex number, but the first number started with 7 or less, then I would only need 3 bits instead of 4 to represent the most significant digit there. So if this were 7B, I could actually fit this in 7 bits if I wanted to. Now, if you typed 8 apostrophe A, if I type 7 apostrophe HAB, then you'll probably get a compiler error from that. I haven't tried that though, but the compiler would probably squawk at you and say that you can't put AB and hex in 7 bits. Or maybe it would just truncate, the first bit. I don't know. I don't know what it would do. You can also just type, 42 without a number of bits, but in this case, it's interpreted as decimal by default, and it says number of bits unsized, but I believe the compilers generally will assume 32 bits. So if you take a value like 42 and you assign it to, say, an 8-bit number, the compiler will give you a warning saying that you're putting 32 bits into an 8-bit value, so 24 of those bits are going to get truncated, but it won't necessarily give you an error. But it's always a good time to specify the bit width. Okay, so anyway, that's all the time I've got. We will continue with the Verilog lecture on next Monday. Remember, we have no class on Wednesday, but unfortunately, that means you're going to have to do the quiz on your own time. I apologize for that. Yes, I will do a review for the final on Monday. I don't want to take the whole lecture, though, because I want to get through more of this Verilog stuff. There are, oh, you know what? I just realized something here. There are some questions on the quiz that involve bit manipulations, which I didn't get to. So I may actually have to move. Let's see how I'm going to do that. I'll have to figure that out. Because if I move the due date for the quiz to be Wednesday, yeah, let's see, yeah, or even like after class on like midnight on Monday, then I won't be able to review it. I'll figure it out. I'll give you an update on that. Yeah, we'll figure something out with the quiz. But for now, it's due on Monday. If you have any questions, send us an email, and we'll see you on Monday. Thank you.